Hello, welcome to the 11th lecture for Math 155. Today we're going to be looking at tangent planes. Now in the last lecture we talked about how to work out the partial derivatives of a function of more than one variable. And today we're going to be applying that knowledge of partial derivatives to understand something called tangent planes and the ways in which we can approximate values close to our function using those tangent planes. And this is called a linear approximation. Okay, so we're going to be talking about what is a tangent plane, what is a linear approximation of a function that has more than one variables. So you should be familiar at the end of this with terms like tangent plane, linearization, and linear approximation. Okay, so what is a tangent plane? Well, let's go back and think about what we have if we have a function of just one variable. In one dimension, we have a curve, and we can describe the tangent to that curve as a straight line that just touches the curve at the particular point that we're interested in. Now, when we have a function of, say, two variables, we have a surface, and we can no longer describe the tangent by just a line. We need to describe this by a plane. And you can think of this as being some curved surface and having a flat sheet of paper that you put against that surface that just touches it at one point. So let's visualize what that looks like. Okay, so here's a surface in 3 dimensions. This is a function of x and y. And what we want to do is work out what does the tangent plane look like that is tangent to the plane at this particular point given by this black dot that I've just flashed on and off there. Okay, so if we visualize that, it looks like this purple surface here. So you can think again about that sheet of paper that is just touching the surface at a particular point. Here it's cropped, but in reality, that plane should go off to infinity in all directions. So as we vary our x or y coordinates, that tangent plane should move around. Okay, so first let's discuss what the equation is for a general plane in R3. So a plane that passes through a point x0, y0, z0, point P, has form some constant a times by x minus x0, so x0 is the x coordinate of P, and plus some constant b times by y minus y0, the y coordinate of P, plus another constant times by z minus z0, the z coordinate of P, and that must equal 0. So that's the equation for a plane that goes through point P. Let's just have a think about why this is the case. Suppose we've got some plane in R3. What this is saying is, if this is our point here, P, x0, y0, z0, then we have some normal vector, which I'm going to call n, given by ABC. And it says that if we take any point in the plane, x, y, z, then this normal vector is going to be perpendicular. It's going to be orthogonal to any vector in the plane. So if we call this vector here v, then our normal vector is orthogonal to v. Okay, so let's work out what this looks like then. So let's write down what our vector is. So our vector v is just going to be equal to, well, the terminal point is x, y, z. That's any general point in this plane. And the starting point is P, which is x0, y0, z0. So that's just going to be x minus x0, y minus y0, and z minus z0. So that's just going to be the equation of any vector in this plane going to a point, general point x, y, z. And our normal vector n is equal to a, b, c up here. So we know that these two vectors n and v are going to be perpendicular. So that means that n dot v, dot product of these, is going to be equal to 0. That's because n and v are perpendicular or orthogonal. So that means that we can just take the dot product of these things. So if we do that, then we're going to end up with a, b, c dotted with x minus x0, y minus y0, z minus z0, and that has to equal 0. And therefore, we're going to have a times by x minus x naught plus b times by y minus y naught plus c times by z minus z naught equal to 0. So that's how we can work out what the equation of any plane is. We just need to work out the point that it's passing through, and the vector is normal to the plane. It's orthogonal to any vector that we have in that plane. So now that we know how to write down the equation of a general plane, we can work out what the equation of a tangent plane is. It turns out it's given by this equation here, and we can see this by working forward from our equation from the previous slide. Okay, so all we need to do is first of all put this in terms of c. So we have c times by z minus z naught is going to equal minus a times by x minus x naught plus, minus b times by y minus y naught. And we can divide through by c, in which case we get a minus a over c and minus b over c as the coefficients here. And we'll just drop those brackets. We can see that this is very similar to what we have circled in red below. So the only difference here is that our minus AC is now replaced by this partial derivative of f of x at the point x naught, y naught. And likewise, our minus BC is replaced by this f of y, the partial with respect to y at x naught, y naught. Now these coefficients up here, the minus AC and the minus BC, are just numbers. So let's call this one A and this one B, lowercase a and lowercase b that is. And we want to see what this means in terms of our tangent plane. Okay, so let's first of all consider what happens in the plane y is equal to y0. So just in this plane here, well, in that case, we're going to have z minus z naught is equal to a times by x minus x naught. So this is just from the slide before, when y is equal to y naught. And that's just an equation of a line. In fact, it's the tangent to the curve. So this is the tangent at z is equal to f of x, y naught. Okay, so all that means then is that our a is going to be equal to our partial derivative of the function at x naught, y naught. Similarly, if we do the same and look at the plane x is equal to x naught, then we have z minus z naught is going to equal b times by y minus y naught. And this is the tangent at z is equal to f of x naught, y. So that's the tangent line, that is, to the curve at this point. So in this case, we just end up with b being equal to the partial derivative of f with respect to y, again at x naught, y naught. So this is where the x naught, the partial derivatives at x naught, y naught come into play. So what we've done is we've taken the tangent plane from the previous slide, the general tangent plane that passes through the point x naught, y naught, z naught, and then we've now looked at what is the tangent plane for a particular function. And we see that it ends up being determined by the partial derivatives at that particular point. Okay, so let's go through an example. Suppose that we've got this function here. Let's call this f of xy, and it goes through this point 1 minus 1, 1. You can check that it goes through that point by substituting in the x and the y values here from this point and seeing that you end up with z being equal to 1, which is the coordinate that we're given. So what do we need to do? Well, if we go back to our equation above, we need to work out what the partial derivative of f is with respect to x and with respect to y evaluated at this point here that we're given. Okay, so let's first of all just work out what the partial derivatives are. So f with respect to x And that partial derivative is going to be equal to, we are going to have a minus x on top and square root of 4 minus x squared minus 2y squared. And our partial with respect to y is going to be minus 2y over square root of 4 minus x squared minus 2y squared. So now that we have our partial derivatives, we just need to substitute in our x and our y values, and we'll pop the values of our partial derivatives evaluated at the point of interest. So our partial with respect to x at 1 minus 1 is just going to be equal to minus 1 over 1, which is minus 1. And our partial with respect to y at 1 minus 1 is going to equal 2 over 1, which is just going to equal 2. So we have these values here, so we can now substitute this in for our equation for the tangent plane. So our equation for the tangent plane, while using what we had above, we need z minus z naught. So z naught is just 1 in this case, so that's just the z coordinate for our point, so this point up here. So this is using our equation from here. So we have z minus z naught, where z naught is 1. This is going to then equal, well, again, let's go back to what our equation is here. So you have the partial of f times by x minus x naught. So it's the partial of f evaluated at x naught, y naught times by x minus x naught. Okay, so our partial of f was just minus 1 evaluated at this point. So that's just this from up here. So we'd have minus 1 times by x minus x naught. X naught here was 1. So that was just this coordinate here. And then we're going to add this to our partial with respect to y evaluated at x naught, y naught multiplied by y minus y naught. So that's this partial here. So 2 times by y minus y naught, and y naught is minus 1. So that's this coordinate here. So minus minus 1. So rearranging, we just end up with z is equal to minus x plus 2y plus 4. So this is our equation of the tangent plane. So now that we know how to write down the equation for a tangent plane, we can do something called a linearization and a linear approximation of our function close to a point on that surface. Okay, so when we carry out a linearization, what we're essentially doing is saying, okay, here is a surface, this describes our function, and we're going to put our piece of paper that represents our tangent plane just touching a point on that surface, and then we want to work out what the value is of our function at a point on that surface a little bit away from where our tangent plane is. And we can say, well, if we zoom in enough, everything is approximately linear. And so if you move just a little bit away from that point, we can approximate our function by what's going on in our tangent plane. And because our tangent plane is just a linear function, it's very easy to work with. So that's essentially all that's going on here. So when we carry out a linearization, what we're doing is we're saying, okay, our linearization L of xy is going to be, this is our, you can think of this as being our z, is going to be our z naught, so is equal to f of ab is our z naught that we had above, and then plus partial derivative of our function at ab in the direction of x, multiplied by how far away from x we are, plus the partial derivative at ab with respect to y, multiplied by how far away from y we are. So this is just our equation for our tangent plane at the point AB, f of AB. And so if we want to make a linear approximation at a point xy, so what is our function value at xy? That's approximately going to be what we have at our given by our tangent plane. So this is just what we have here. Okay, so we're going to approximate our function by a tangent plane. Okay, so this is an example here. So let's find the linear approximation to z at a point 1, 2, where z is given by this function here. So I'm going to call this f of xy. just keep the notation the same as we had before. And we're going to use this linear approximation to calculate a value a little bit further away. So we're at a 0.12 and we want to see what is the value at 1.06, and x is equal to 1.06 and y is equal to 1.97. So we've moved a little bit away from that. We've not moved too far away. If we move too far away, then our linear approximation is not going to hold. But let's see if we can calculate a linear approximation and see how close it is to the real thing. So the first thing we need to do is we need to work out our partial. So our partial with respect to x of this function is just going to be 6x squared minus 9y. And our partial with respect to y is going to be 6y squared minus 9x. And then, if you remember, we need to evaluate each of these partials at the point of interest. So we take our point 1, 2, so we need to evaluate our partial with respect to x at x equal to 1, y is equal to 2. And this gives us minus 12. And we do the same for our second partial with respect to y. And this gives us 15. So these are the coefficients that we're going to have in our linearization. So if we write down what our linearization looks like, our L of xy is just going to equal, let's go back to the slide before, we're just writing down this here, f of AB, so AB is going to be our 0.12 here. So we need our function evaluated at the point, so that's going to be f at 1, 2, plus we had our partial with respect to x at 1, 2 times by x minus x naught, or in this case, x minus a. So that's this bit here. So a in this case is just going to be equal to 1. And then we do the same, but in the y direction. So we're going to have, sorry, this should have been, no, that is correct. So we have fy, a partial of f with respect to y, evaluated at 1, 2, times by y minus y naught or b, and that's equal to 2 here. So we've worked out what our partials are evaluated at the point 1, 2, so we can substitute everything in now. We can see as well that f of 1, 2, if we calculate f of 1, 2, that's going to be equal to 2 times by 1 plus 2 times by 8 minus 9 times by 1 times by 2, and that works out to be 0. So this is going to be equal to 0 minus 12 x minus 1 plus 15 y minus 2, where I'm just substituting in the values for the partials as well as f of 1, 2. So that's our linear approximation. Sorry, that's our linearization. And then if we want to make a linear approximation to a particular point, then we're going to say, well, our linear approximation to f at 1.06, 1.97 is going to be approximately equal to our linearization at that point. So that's going to be approximately equal to L of 1.06, 1.97, which is equal to 0, minus 12 times by, we'll sub in our x value, 1.06 minus 1, plus 15 times by 1.97 minus 2. Note that the things in the brackets are generally going to be small, so these, just highlight these values here, we should always want these to be quite small because we want to be quite close. When we work this out, this ends up being about minus 1.17. And then if you work out the actual value, so this is our f at 1.06, 1.97. Our actual value is minus 1.12. So this is pretty close. Okay, so the reason we might want to do that, you say, well, okay, well, we already had our function. Why don't we just plug in our x and y values and get the exact value? We're going to see that we don't necessarily always have a function that we can work with, or our function might be incredibly complicated and we can work out a very simple linear approximation to that function that's a lot quicker to calculate. So although in these sorts of circumstances, it might seem obvious that you would just substitute in your x and y values and get what you want out of a calculator, that might not always be possible, or it might be a lot faster to use a linear approximation. Okay, let's go through another example. So we want to linearize this function here around the point 3, 0, and use it to approximate the value of our function a little bit further away. Okay, so let's work out our partials. So we're going to have our partial with respect to x is going to be 2 times by the square root of x plus e to the 4y. And our partial with respect to y is going to be 2 e to the 4y over square root of x plus e to the 4y. And then if we evaluate each of these at our point 3, 0, then our partial with respect to x at that point is going to be 1 over 2 root 3 plus 1, which is going to be just 1 over 4. And our partial with respect to y at this point is just going to be equal to 2 over root 3 plus 1, which is just going to end up being equal to 1. So if we calculate our linearization, our L of xy is going to be our point f evaluated at 3, 0, plus our partial at 3 with respect to x at 3, 0 times by x minus the x coordinate value. So that our point is 3, 0, so it's going to be x minus 3. And then add this to our partial with respect to y at 3, 0, multiplied by y minus the y coordinate, which is 0. So our linearization then just ends up being 2 plus a quarter of x minus 3 plus y. So now we can carry out our linear approximation for our function at the point 3.1 minus 0.1. That's going to be approximately equal to our linearization at 3.1 minus 0.1. And that's just equal to 2 plus a quarter of 3.1 minus 3 plus y, which is just going to be minus 0.1, which works out to be 1.925. Again, if you work out the actual value, this ends up being 1.94. So again, these values are very close to each other, so our linear approximation is pretty good. You'll find that if you tried to take a linear approximation further and further away, suppose you tried approximating the using this function to approximate f of, say, 10 minus 3, you'd see that this would be very far off. Okay, so this linear approximation generally only works when you're quite close. We can also apply the same logic to a function of more variables. So essentially the hard step is going from one variable to two variables, but then once we know what we're doing with two variables, it's really the same as when we have 3, 4, 5, any number of variables. Okay, so we say that the linearization of a function with 3 variables, x1, x2, and x3, is going to be equal to our function evaluated at a point ABC, which is close to our x1, x2, x3. So our linearization of f at that point ABC is equal to the function value at ABC, plus our partial with respect to the first variable, x1, evaluated at ABC, times by x1 minus a, so how far in the x1 direction we are away from a, and then exactly the same for x2 and x3. So our linear approximation in any number of dimensions is just a direct continuation of this process. And likewise, our linear approximation of f at ABC is just going to be f of xy is approximately equal to this linearization here. So to go through an example of this, if we have this function of 3 variables, x e to the y z, and we want to find the linearization of f at the point 1, 0, 0, and use it to approximate a point close to that, well, let's first of all work out f of x, y, z is equal to x e to the y z. So f at 1, 0, 0 is just going to equal 1. And then if we work out our partials with respect to x, y, and z, so fx at x, y, z is going to equal e to the y z. Fy is going to be equal to xz e to the yz, and fz is going to be xy e to the yz. And then we evaluate each of these partials at point 1, 0, 0. So our partial with respect to x at 1, 0, 0 is just going to be equal to 1. And then our partial with respect to y is going to be equal to 0, and our partial with respect to z is going to be equal to 0. So if we do our linearization now, then our L of x, y, z now is going to be equal to our function at the point 1, 0, 0 plus our partial at, with respect to x at 1, 0, 0 times by x minus 1, because 1 was the point, the coordinate of our point where we're carrying out our linearization. And then we add on the corresponding partial with respect to y, evaluate at 1, 0, 0 times by y minus 0, because 0 is the y coordinate. And then similarly for z. But we know that our partials with respect to y and z at this particular point are equal to 0, so these last two terms just drop out. So this is just going to be equal to 1 plus x minus 1, which is just equal to x. So our linearization of this function that looked quite horrible, our linearization at the point 1, 0, 0 is actually just x. So it's very straightforward. So if we want to do a linear approximation of this function, what is our f at 1.1, 0.02, minus 0.05? Well, it's approximately given by our linearization at 1.1, 0.02, minus 0.05, which is just equal to 1.1. If we look again at what our actual value is, if you plug these numbers in, you end up with 1.098. Again, these two things are very close to each other. So this is an example where if we have what looks like quite a nasty function, x e to the yz, we can work out our linearization at a particular point, and we've ended up with a much simpler calculation to do. It's just equal to x in this case. Okay, so make sure you are familiar with all the terms that we've gone through today, particularly what is a tangent plane, how do we calculate this, what do we mean by linearization and a linear approximation to a function at a point. Okay, thanks very much, and I'll see you at the problem class.